the Centre for Organic Photonics and Electronics, which is a joint venture between the School of Mathematics and Physics at the University of Queensland and the School of Chemistry and Molecular Biosciences. So this afternoon it's my pleasure to chair a session which is basically divided into two bits. There's the first bit by Dan Cox, and you see Davis, and he's going to be talking to us about sustainable energy and why we need it. And that's actually going to take up two sessions. So the second session that he's going to talk about, which was effectively different forms of photovoltaics, he's going to pick up on that tomorrow. So there are two sessions on sustainable energy, and then later on we're going from Warwick Bowen to do with the part 3 and part 4. So I'm sure after part 1 and 2 we're riveted in part 8 for the final sessions of the soap opera, which is to do with whispering something or other. Whispering mode galleries, so that's right, whispering gallery modes. So, Dan, please.
Okay, thanks. So I'm the co-director of ICAM, so all of the successes and problems you have with ICAM, now you know who to either praise or blame. And I'm also a professor of physics at UC Davis. And Yvonne asked me to come and give some talk about sustainable energy, partly because this is something that ICAM wants to move into the area of novel materials for energy purposes. And I think very much along the lines of forefront research. And one thing we have to acknowledge, and it's great to have the Organic Photovoltaic Conference starting in a couple of days, because here in Australia, some of the best research on photovoltaics is going on. So my own research is actually on biological physics, but where I can talk about sustainable energy is because I've been teaching a course for about 14 years on energy and the environment, mostly at Davis, and 1 year at Ohio State when I was a professor there. And so first I want to give an overview of the need and availability of sustainable energy. That's the lecture today. Then in the lecture tomorrow, I'll combine some ideas about bio-inspired photovoltaics and nanoscale photovoltaics as clearly places where there's exciting research to be done. I am going to give my own view of that, and I'm not a researcher in the field, and you will be getting many of the best photovoltaic researchers in the world here at the meeting starting on Wednesday, so you can ask them a lot more questions. A great resource for this also is Nate Lewis's web pages on energy at Caltech. He gave a wonderful lecture to us at the ICAM annual conference that Yvonne heard in Davis. He actually gave it from Caltech, but it was a wonderful lecture, and it's a great resource for information on alternative energy. So for today, an overview is basically that technological societies like Australia and the United States and the ever-growing emerging economies and nations need energy. And right at the moment, about 85% of our energy is fossil fuel-based. But the easily accessible reserves of oil, natural gas are running out. And although in the United States they talk a lot about clean coal, the reality is coal is never very clean. I suppose that's a big issue here in Australia as well, which I know is a big coal producer. Climate change is a real concern, which again maybe felt very acutely here given the drought situation in Australia. And it's in essence an uncontrolled experiment on the world. And of course the biggest contributor to climate change is the carbon dioxide produced by the fossil fuels. So what do I mean by green energy? That's nearly greenhouse gas neutral energy. And so here's an overview of the ideas that I'll be talking about, trying to, in some sense, make the fossil fuels green by sequestering the carbon dioxide, and then nuclear, hydro, biomass, wind, and solar. Most of my energy is spent on discussing nuclear, wind, and solar. And then caveats, a couple of caveats at the end here. So feel free to interrupt me with any questions you might have, but I want to just stimulate the discussion and hopefully get people thinking about this as to why ICAM is interested in why having now our second meeting on energy, one in China earlier this month, why we're quite excited about moving this direction in ICAM. So first of all, just in terms of energy usage, the U.S. consumption per year overall of energy is about a quarter of the world's consumption, and we consume about 98 quadrillion BTUs, or about 10 to the 20 joules, which corresponds to a demand of 3.3 terawatts. If you change that to watts. And in terms of source overall for energy, the world and the US don't look very much different. There are some differences, but what you can see, if you add up these three pieces of the pie right here for coal, natural gas, and oil, about 85% of the energy usage in the US and in the world is fossil fuel based. And that basically means 85% of our economy, because there's a one-to-one correspondence basically between the energy and the economy. So 85% of the economy basically is fossil fuel driven. That means that any change on this is going to be darn hard to accomplish. You know, there are some differences. We have a little bit more nuclear in the US than worldwide, and of course, if you looked at this for France, France would have a lot more nuclear, for example. Renewables occupy a bigger slice in other parts of the world than in the US. But basically, you can see in terms of the fossil fuel part, we're in lockstep with the rest of the world, and we've got 85% of it tied to fossil fuels. That's huge, and yet this is where we have to probably change, as I hope I'll convince you of. If you look on a country-by-country basis, again, you can see some of the differences, but the biggest consumer, it's about to change, but the biggest consumer of in millions of tons of oil equivalent of energy is the United States. And again, this is a breakdown in terms of like oil, natural gas, coal, and nuclear energy. The next biggest is China, then the Russian Federation, Japan, India, on down to Brazil. This is of, I can't remember which state this was, this is just a few years ago. But these are the 12 biggest energy consumers right here. Okay. And here's the transit energy consumption. What's interesting about this is you go from 1990 to 2006 in terms of the millions of tons of oil equivalent for all of these different countries right here, is that actually it's relatively flat with but two noticeable exceptions. One really big exception, and that's the blue right here, which is China. Not surprisingly, China's economy is growing at great leaps and bounds, and therefore the energy consumption is also going up. And it's not as noticeable, but if you look at the black one, there's also an increasing width of the black band here, which corresponds to India. So these two large economies of the emerging world are consuming more and more energy. And of course, it's still, most of that is fossil fuel based. Now these represent time series points for gross domestic product and energy consumption. And over a number of years for the United States, while the gross domestic product has gone up, the relative energy consumption stayed pretty flat, which is true also in the European Union and Japan. Whereas in some of the emerging nations like China and Brazil, there's a direct linear increase of the energy consumption per capita with the gross domestic product, the per capita amount of money made by that country, basically. So this tells us a couple things. One is it tells us that, again, energy and money are basically interchangeable, although once you get to a developed economy, you can, through conservation efforts, basically keep pushing up your gross domestic product while maintaining a fairly constant energy consumption. On the other hand, it also tells us, since the standard of living isn't really so much different between the EU, Japan, and the United States, it tells us that you can even do a lot better, certainly, than the United States. And Australia is also down more like this. The United States and Canada are up here. We're relative energy hogs compared to the rest of the emerging, or the rest of the developed country. But so there is an economic issue that a lot of countries which may be contributing now in a higher way to the greenhouse gases, for example, still on a per capita energy consumption basis are quite low. Okay. And this is an interesting chart which is very hard to read, but this is the electrical energy consumption per state in the United States. California, the biggest state where I come from, and the most populous state, and the largest economy of any state, has actually the lowest per capita electrical energy consumption. The The highest per capita electrical energy consumption is Wyoming, which is the state of this guy, Dick Cheney. And very famously in the early 2000s, when California was going through a quote-unquote energy crisis, it was really a deregulation crisis, where basically we were getting ripped off by companies shifting power out of state and then reselling it to California at extraordinarily high rates. This guy made the statement that conservation may be a sign of personal virtue, but it's not a sufficient basis for a sound, comprehensive energy policy. Well, I do have to agree it can't be the only thing you put in a sound, comprehensive energy policy, but the truth of the matter is California helped to conserve its way out of this energy crisis, so conservation is something we should always keep in mind. And again, that's illustrated back here, where some economies which are basically comparable to the United States per capita wind up using a lot less energy per capita, so that we don't have to be energy hogs to be up in here. Okay, oh, there he is again. Now just a little bit more. The way that energy usage is broken down in the United States, and there's similar breakdowns in the rest of the world, is that about a quarter of it is used for transportation, and that's where the oil basically goes. Oil, to a first approximation, is not used for electrical energy. And that's an important point, because often, at least in the US press, I don't know if you get better reporting here in Australia, but in the US press, often people say, well, we need alternative energy to oil, so let's get nuclear power. Well, that only works if you've got electric cars. And we don't have electric cars in the United States. There's often an interchangeability of oil with other forms of energy, and in reality, in practice, that's not true. So then, here is where a lot of the electrical generation goes, although there's quite a bit of natural gas in the heating and in the cooking and so on that would go on in here as well, in residential, commercial, and industrial use. But a lot of the energy consumption is in here, and transportation is about a quarter of it. That's where the oil goes. And in terms of electricity production in the US, what we have is about half of it coming from coal, about nearly 20% coming from natural gas. There's no oil on here, as you notice. 20% from nuclear, 7% from hydroelectric, and 6% from renewable sources. Obviously, this will change some depending upon the country, but that's the breakdown in the United States. This changes a lot if you look at California. In California, the biggest fossil fuel contributor to our energy is natural gas. We have a lot of natural gas power plants in California. We have some coal. The coal is always from power that's produced outside of California and then shipped in. I'll make a point on why this different breakdown is important at the very end of the talk, as an example with electric cars. So this is where we start to get in why we need it to change. First off, we're going to run out of fossil fuels. We have a lot of resources of coal, but we're really pretty low on what's easy to get to in terms of natural gas and oil. So we're going to run out. So one question is this the energy curve of history? If so, we're in big trouble, because this would represent basically the fossil fuel curve of history. I mean, the Industrial Revolution kicks in, and then somewhere over here, maybe in the next 150 years or so, we start to really peter out of those fuels. Yeah?
What's the dip in the middle?
That's a good question. I don't know for sure what that is.
Oil prices.
Oil prices?
74.
So the easily extractable resources of oil and natural gas are dwindling. This is a nice chart made by Nate Lewis in one of his presentations. And what you can see here is that unconventional sources of oil and natural gas are in yellow. Conventional sources of oil and natural gas, mainly by drilling, are in blue. And what you can see is that in terms of the reserves of oil and natural gas, these are the estimated reserves. These are possibly all obtainable resources of oil and natural gas. In terms of the reserves, most of it is in the exotic forms, the hard to get to forms. That's not true of coal, but and there's a lot of coal. So if you look at how many years we would have available at 1998 consumption, if you include the exotic sources, we've got at the order of 40 to 78 reserves of oil, maybe up to 180 years of gas and a couple hundred years of coal. Depending upon how much we can tap into those other places, here's how high you could potentially make the numbers. But basically, we've got probably a few hundred years of coal and of the order, ballpark of 100 years of easily get to oil and natural gas. We're going to run out. And here's just, this is typical of mineral resources. An example, a historical example from the California Gold Rush. When it started in the California Gold Rush, you could just pan for gold in the streams and get gold. But as time went on, they had to move to other methods, and they started doing hydraulic mining of the High Sierra, blasting away the slopes to reveal the gold, with water being forced at high speed to blast away the slopes. That actually led to the first environmental lawsuit by farmers in the Central Valley of California who sued the miners and stopped hydraulic mining in the early part of the 20th century. And then in more recent times, one of the last operating gold mines in California was the McLaughlin mine, not too far from Davis. It was an open pit mine, and much to the credit of the mine operator, they're doing a very good job and planned on it even before the mine started operating for restoring the land around the mine. But this mine was proud to get a half an ounce of gold for every ton of ore. So as time goes on, it gets harder and harder to extract mineral resources, whatever their form is. It's harder and harder to extract them. And that's what's going on with oil. This is a famous guy who's relatively hard to find in the internet, actually. I think because of obvious reasons that people don't want to believe that this is, or suppress that this is probably going on. But this is King Hubbard, who was a petroleum geologist in the mid part of the last century. He predicted that U.S. oil production would peak about 1970. And as a matter of fact, it did. As a matter of fact, U.S. oil production peaked right here. And basically, we're on the downside of the United States, and so that's why the United States is consuming ever more of its oil from imports. Whether that's going on in the rest of the world still remains kind of controversial, but it definitely happened in the United States. And all Hubbard did was use the logistic equation. This has been used for describing populations where you have an initial exponential growth, and in a population, as there starts to be competition for resources, you get a minus p squared term, but this represents the difficulty in extracting the resources in the case of applying this to mineral resources. And it gives a simple solution with this exponential or Fermi function-like form and a peak production rate. And so Hubbard just basically used the data to figure out where the peak in the production rate would occur. And it could apply to any limited resource. Gold, it applies to the Ogallala Aquifer in the United States. If you extract the water faster, then you can replenish it, which is true. That aquifer underlies Colorado, for example, where Elam and his students live. So that's all that Hubbard did. But we also have visual evidence that we're running into the limits. For example, this deep sea drilling at the depths that the Deepwater Horizon disaster has taken place. This deep sea drilling is relatively new, and you have to drill down enormous distances to get to those oil deposits. This is harder to get to oil than we had in the past, like from Saudi Arabia, for example. This is something else that's going on in the United States, fracture-based extraction of natural gas in the United States. There's actually a movie documenting this, and what you're seeing in this picture, and I hope I can get this YouTube clip to work, is this is tap water, and the guy's actually taking a barbecue lighter and lighting his tap water on fire. And basically, to get to this natural gas, they're fracturing the land underneath the natural gas, underneath these communities. And the natural gas from that fracture drilling is then seeping out, and you'll see here in a minute, there it goes. You can actually light it on fire. It's not just natural gas that's coming out. In order to do the fracture mining, normally they just pump down water, but often they pump down other things. They used to pump down diesel oil to get the natural gas out. So the point is that to get to this hard-to-get-to natural gas with this fracture drilling technique, you pump stuff down. Some of it has nasty toxic chemicals in it. It winds up seeping back into the water supply, and the natural gas seeps into the water supply as well. You can find on YouTube clips of people who will tell you they're afraid to take a shower with the lights on because they don't want the electricity to ignite the shower while they're in there. And then, as I said, there's a documentary here called Gasland, which just is showing in the States on HBO. Also, you can mine, one of the biggest sources, which is actually reasonably cost-effective, is tar sands, where the oil is mixed in with clay, sand, water, etc. You basically have to mine and separate the oil from this stuff. A lot of the oil in the world is actually in this form. The estimate is that there might be 2 trillion barrels of oil in this form of the tar sands. but it basically takes 2 tons of the tar sands doing 1 barrel of the oil. That's getting to be closer to that mentioned, like the gold. The biggest deposits are in Alberta and in Venezuela. There's some large deposits in the US and Utah. It's not real popular. There's a lot of NIMBY action around the tar sands mining, but it is in Alberta a very viable production method for oil. And to extract the oil from the tar sands, you've got to use huge amounts of water, either in separation post-mining or in situ extraction. Large amounts of energy involved in the extraction. And the estimates of how much energy you produce range from about 1.5 to 5 to 6 times the energy you put in. Obviously, this is not as an effective way of extracting oil as when you're just drilling down and having the oil gush back out. Shale is also available, and so far that's always been a bridesmaid for oil production. Colorado and Wyoming have huge shale deposits, maybe 1.2 to 1.6 trillion barrels of oil in Colorado, Wyoming, and Utah. In principle, extractable are probably 800 billion barrels of oil. You can, in principle, mine it and extract it from the mined stuff. Then you're going to devastate the landscape of these western states. Or you can process it in situ. So far, it has not proven commercially viable, but whether we're driven to this by the market economy, if we don't change the direction of things, is an interesting question. Coal in the U.S., as I said, there's a lot of talk about clean coal. I'm not sure how coal plays out in Australia. But in the United States, there's a lot of talk about clean coal, but it's an oxymoron. Clean coal meaning that you extract the carbon dioxide from it, you extract the pollutants like sulfur from it that are byproducts of the coal burning, and you therefore have a quote-unquote clean coal. Well, wherever you take the coal from is going to be a disaster. They basically are blowing off mountaintops in West Virginia to get to the coal. They're doing large open shallow mines and pit mines in the western United States to get at the coal. So it leaves big scars on the landscape. It's relatively easy to extract it in the sense that it's often very close to the surface, but it leaves big scars on the landscape. And things are much improved on this front in the United States thanks to aspects of the Clean Air Act in the United States. But one of the big problems in the U.S. is that the eastern coal particularly produces a lot of acid from the sulfur that's present in it. So you actually wind up making sulfuric acid in the atmosphere. And these are showing the low pHs in orange, normal pH is basically in green. These are showing the pH levels that you can find in groundwater, rainwater in the northeastern United States. A little pocket of it here from the Four Corners power plants in Colorado. But the coal in the western U.S. tends to be relatively sulfur-free, and the coal in the eastern U.S. has high content of sulfur. And so this is one of the problems. And the acid doesn't necessarily go up into the atmosphere only. In the eastern United States, where there's coal mining, then one typically finds acid drainage into the mines, into the streams around the mines. So this yellow stream is made yellow by acid drainage from the mines. I believe this stream is in West Virginia. So my point about this is we're going to run out of the resources. They're pretty dirty, although some of the things we're going to do for alternative energy aren't necessarily clean. And as if that wasn't bad enough, they also are the main contributor to climate change. So this is giving, from the U.S. National Oceanic and Atmospheric Administration, this is giving time series of temperature combined for land and ocean, the average over the oceans from basically the 1800s, late 1800s up, and then land from the late 1800s up. Because of the thermal inertia of the oceans, the overall temperature change in degrees Celsius of the oceans has been smaller, of the order of ½ a degree Celsius, and on land it's been of the order of about a degree Celsius between the Industrial Revolution and the present time. And of course, we can trace that to the carbon dioxide, because carbon dioxide is a heat-trapping gas. And there's a basic law of chemistry that every time you burn a hydrocarbon, like CH4, natural gas, approximately CH2 for oil, approximately CH for coal, for every hydrocarbon burned, you release 1 carbon dioxide. That's basically an immutable law of chemistry. Of course, in an atmosphere with more than oxygen, you can produce some other products, but basically you get 1 carbon dioxide for every hydrocarbon you burn. So the release of carbon dioxide into the atmosphere from the burning of fossil fuels is just unavoidable. You can't avoid it. And in fact, basically, The greenhouse effect is something we need to keep the planet warm enough for habitability. If we didn't have that layer of greenhouse gases, we'd be way too cold. By about, the mean temperature would be on the order of 250 Kelvin on the surface of the Earth without these greenhouse gases. But what we're doing with the global warming is that we're enhancing greenhouse gas contribution, the heat trapping gases in the atmosphere, especially these guys right here. And the biggest single culprit is carbon dioxide, which again is completely tagged to the fossil fuels. So the numbers of carbon dioxide we have up there, given residency time of the order of a few decades for carbon dioxide, completely traceable back to the burning of fossil fuels. And that raises an important question when you get back to the emerging nations, that most of the carbon dioxide that's up there right now is from the developed nations, because we put it up there decades ago. So what's going up more recently, even though China has passed the US as the leading greenhouse emitter, still most of the greenhouse gases that are up there are from developed nations. So what is the responsibility of developed nations to help out emerging nations in this regard? That's an interesting question. And you know, these ice cores actually go back about twice this distance now. But these are interesting time series of temperature over Antarctica in red, atmospheric carbon dioxide concentration from trapped bubbles in the Antarctic ice in black. So the temperature goes over here relative to the present climate. The carbon dioxide is on this scale, and then in addition there's trapped methane in blue, which is this scale right here. And the basic kind of baseline of carbon dioxide over the last 400,000 years, it's not much different over 800,000, it's, you know, somewhere in the ballpark of 250, 270 parts per million. And right now, we're up here almost to 400 parts per million, and it's all happened in the last little blip. It's show up like a delta function spike on this curve right here. Of course, this doesn't prove, with these time series, one doesn't, you know, there's a causation correlation issue going back in time. But what's very clear is that putting such a large spike represents an uncontrolled experiment on the Earth's climate system. We just haven't seen a spike in carbon dioxide like that going back for 800,000 years. This also gives you an idea that the swing in temperature between the cold ages and between the warm ages is only of the order of 8 degrees. So 1 degree is already a pretty significant part of that. You know, that's part of the point there. Okay, let's see. Now, there's questions about whether warming is really happening besides those temperature series. But the NOAA people who are housed in Boulder will show you plots like these. This is the extent of Arctic ice cover in 1979. This is the extent of Arctic ice cover in 2005. You can see they're quite a bit smaller. And many recent reports show accelerated melting of land-based Antarctic and Greenland ice. That's of great concern because if you melt the land-based ice caps, you can raise the sea level. If those melt too fast, they could give a very significant rise in sea level. I live on a hilltop in San Francisco, so I'm actually pretty safe, but some of my friends might be in trouble. This is Nate Lewis right here, standing in front of a glacier from basically 20 years ago and now more recently. Here's a glacier in Argentina. This is about 1928, and this is 2004. You can see the glaciers in tandem with the Arctic ice cap. The glaciers are retreating. And you can ask, I mean, one of the popular ways to try to, I don't want to go, I mean, I could spend hours and hours talking about climate change, and I don't want to do that, but one of my favorite ways of pointing out that there is actually a fingerprint to anthropogenic gas-driven climate change is to look at graphs like these. So these are computer experiments, and these are observations. These three are computer experiments, these are observations. This is the vertical profile versus latitude of the warming in the atmosphere. From yellow to red represents warmer temperatures. From light blue to dark blue represents cooler temperatures. The general pattern you can see from observation is that we get a warming in the lower atmosphere and we get a cooling in the upper atmosphere. This is what you get if you put in, let's see, this is if you put in changes in carbon dioxide only. You do reproduce the general trend of cooling up here and warming down below, but you don't get it quite right. If you put in changes in carbon dioxide plus changes in sulfates in the atmosphere, basically suspended sulfates in the atmosphere, you do a little bit better, but again, not so much different. If you now take into account the depletion of the ozone layer, also caused by us from the chlorofluorocarbons in the atmosphere, then you get a much better agreement. Now, the agreement is certainly not perfect, but I want to just highlight this point. Qualitatively, there's a cooling in the upper atmosphere and a warming in the lower atmosphere. What's often cited in the United States by climate skeptics, who are a fair industry in the United States, is to say, well, gosh, this global warming could just be caused by solar variability. Here's the problem with that. Solar variability basically warms up the lower atmosphere by pumping in more heat, which is then trapped in the greenhouse gases that are already present in the lower atmosphere, and leaves the upper atmosphere essentially alone. This is a computer experiment where you do solar variability alone to get a significant temperature rise in the Earth's atmosphere. If you do an experiment where you put in heat-trapping gases to get the same temperature rise, then you get cooling in the upper atmosphere because you're basically not changing the solar flux, you're not changing the amount of sunlight into the Earth, you're changing the amount that you trap in the lower layers because of carbon dioxide, for example. And that means that you're robbing the energy that could go to the upper atmosphere and thereby cooling it more. So this qualitative difference between the usual culprit for warming pointed out by skeptics and warming that's observed in context with anthropogenic gases is, I think, a real important fingerprint of the fact that we're more likely seeing anthropogenic-induced climate change right now. But you don't have to take my word for it. You can go to the IPCC website. Okay, so we're going to run out of fossil fuels. Fossil fuels burning causes, apparently, is a main contributor to climate change. And so that certainly suggests that we have some painful choices to make. And this graph kind of exemplifies those painful choices. I guess I don't have I should pull up a clock because I don't know how I'm doing in time.
It's okay, we've got another 10 minutes.
Oh, okay, so 10 minutes, yeah, okay. So this is from Nate Lewis also, and it's very illustrative. The idea is if you want to eventually stabilize things at a carbon dioxide concentration of 350 parts per million, 750 parts per million, or just don't change the thing and let business as usual run ahead, with increased consumption of energy associated with increased population growth and increased economic development, these curves sort of give you the baseline choices. This is the world power consumption in 2005, right here. This is the increases in carbon-free primary power over here. In order to sustain the projected levels of population and economic growth, but to get the carbon concentration down to 350 parts per million in a longer haul in the atmosphere, we would have to choose a blend of carbon-free energy sources that would look like this curve right up here in terms of the generated energy. If we want to do business as usual and basically grow carbon-free sources to match some of the increased demand, that will give you this curve here, and that takes you up to like 1,000 parts per million. So you can see there's a range of choices you have to make about alternative energy, but even if you don't accept the climate change, you're going to have a pretty significant increase in alternative energy sources in order to meet the demand. This is also taking into account the depletion of the fossil fuel sources. So this is basically a computer simulation running into the future with increased economic demand for energy, increased population growth, and also taking into account the available fossil fuel resources. And if we want to get up here, which would actually take us below the existing carbon dioxide levels we have in the atmosphere right now, we got to consume by the year 2100 of the order of 48 terawatts of power, all from alternative energy sources. And at the moment, we're consuming worldwide about 14 terawatts of power. So it gives you some idea of the difficult choices that are ahead of us. So the combination of depletion of the oil, wanting to reduce the carbon dioxide emissions, drives us towards, and wanting to maintain technical societies and new technical societies in China and India and Brazil and elsewhere, that forces you to make some very tough choices and forces you towards some kind of alternative energy. And so then I guess the next thing is where to go with that. But maybe I'll break here and see if you have any questions or comments so far. Thank you.
Thank you for the fingerprint. the last plot you showed, I noticed that it said that it was projected for population growth. It seems like in the New Scientist magazines in our household restroom, what is usually being discussed now is population implosion.
Oh, you mean because of scarce resources and so on?
No, because of contraception. Women all over the world are having less babies, it seems. So,
Right. So it would be interesting to run a scenario where you assume, I actually don't know for sure what numbers for growth are assumed, population growth are assumed here, but it would be interesting to run something for like presumably because of decreased fertility via contraception, decreasing population out here. But there still would be potentially increasing economic demand for the energy, right? As the emerging nations, as the emerging economies develop. So, but I don't know. I actually should dig into this and find out what are the detailed numbers assumed in here. But and that I don't know. But it just sort of gives you a nice summary of the choices that we have to make.
it's pretty stark.
It's pretty stark.
Yeah.
Yeah. I think was there a question? There was a question back there. No? Yeah.
I think I've heard the same talk from Dr. Lewis, and just I would take the beginning of your talk and the end and ask you how you reconcile these. He points out that the atmosphere is an integrator of CO2 with about a 20-year time constant. And so conservation doesn't, in that sense, in the sense of climate change, doesn't actually help because the only way to stop CO2 going down, or to keep it to go down, is to not burn it.
Yeah, exactly. Yeah.
So,
So this scenario, if you actually look at it, requires that we start cutting hugely back on CO2 emissions now. I mean, if you actually look at the way that this would show up on the CO2 emissions, it's a big, huge drop on the CO2 emissions. Yeah.
Oh, one more. So we know fossil fuels and oil is finite. So if we burn all that oil, do we know what CO2 parts per million we end up with?
Yeah, the business as usual scenario, this one winds up, as I recall, at about 1,000 parts per million. That means we keep burning fossil fuels, et cetera. That winds up at about 1,000 parts per million by 2100.
Is that
Which is
assuming
pretty bad.
finite resources?
I'm sorry?
Is that assuming finite oil?
I believe so. Yeah, I believe so. Yeah. But as you say, it's then once you get it to those levels, it's pretty hard to. It takes a while to bring it back down. It certainly takes a while to bring it back down.
What do you see as the effects of carbon dioxide absorbing in the ocean?
Oh, that's another big point. That whenever people talk, that's another big point. There's big efforts to want to climate engineer, right? So, for example, let's pump a bunch of soot up into the atmosphere above Greenland, and then we can control to cool the atmosphere because we're pumping soot up there. But that doesn't change the fact that the carbon dioxide is making the oceans more acidic. This is clearly happening, and that increased acidity of the oceans makes it very hard for the shell making organisms like coral and shellfish and so on, but especially coral, obviously. It makes it very hard for them to function. If the pH gets too low, it'll just wipe out the coral reefs. They won't be able to maintain. And where we're at in that, I actually don't know for sure where we're at on that, but clearly you increase the acidity of the, there's a basic acidity to rainwater, which is set by carbonic acid, by CO2 dissolving into rainwater, which is around 5.65, if I remember right. So, but clearly increasing the carbon dioxide concentration is going to increase the carbonic acid concentration in the oceans, and it's a huge problem, absolutely huge. And that's another reason to stop. Even if you didn't believe global warming, if you believe that we should have viable oceans, you should stop. We should stop. I'm sorry, yeah.
So can we make some another reversible process, like to take carbon dioxide from the atmosphere and convert it to some other suspension?
Yeah, and there's a couple of, there is the idea of carbon sequestration, but there also is the idea of just of taking the carbon right out of the atmosphere, putting in a bunch of machines that basically suck carbon dioxide out of the atmosphere. Or you could try to, another idea is you could try to stimulate algae growth by pumping massive amounts of iron into the oceans, and then they could suck in more carbon dioxide. But then what effect does that have on the oceans when you have massive algae blooms from the stimulated? But yes, that's another idea to try to capture carbon dioxide. But again, it's going to require sort of a huge experiment. and a huge, very expensive to scrub the carbon dioxide. But it is an idea. We may have to do something like that to prevent the oceans from getting destroyed, or to try to bring down those, just like what you were saying, to try to bring down those concentrations.
I mean, I think people are also working on various photocatalysts to convert carbon dioxide, say, into methane and water.
Yeah.
And then we produce an energy source.
Of course, when you burn that methane, you put it.
I know, it's a cyclical process, that's
Yeah.
very true.
Yeah.
But it also doesn't use so much energy in terms of electricity to generate. But I mean, to do that on a massive scale is
Yeah.
an interesting engineering problem. And at this stage, I don't think there's a catalyst that will do that particularly efficiently. Go.
Yeah, you just showed the graph of the last 800 years, the carbon, the
Oh,
amount
the last 800,000 years, yeah.
of 1,000 years, yeah.
Well, this is 400,000, but you can find graphs now that look very similar going back 800,000 years.
So I'm
Yeah.
just wondering why the amount of carbon dioxide just increase and then decrease again. What's the reason? Why
Oh, well, almost certainly what drives these are the Milankovitch cycles. Okay, so those are the main planetary cycles that drive the cooling and warming cycles of the Earth are, let's see, one is that there's a precession in when the Earth, when winter corresponds to the part of the Earth that's on the closest approach to the Sun, and when it might correspond to where it's on the furthest part of the Sun, there's a precession in the Earth's axis, so that changes the exposure of the northern hemisphere, especially to the Sun. Gosh, what's the third one? Anyway, these cycles are basically tens of 100,000 year cycles, and those cycles are what produce these periodic ice ages, basically. So those are pretty well understood geological timescale cycles. And it happens that the carbon dioxide and methane flux on those same cycles. So the carbon dioxide is not causing the temperature change here. It's these planetary cycles that are causing the alternation between warm and cold spells here. Where the carbon dioxide comes in is important presently is that, again, if you look at these historic levels of carbon dioxide, we're way up here. If you saw Al Gore's movie, he has a huge huge projection of this graph, and then he gets on a lift and he goes from here up to here, to show where we're at right now. I mean, basically that's the issue right now. But anyway, these cycles are caused by the fluctuations in planetary orbit and in planetary axis of the Earth.
Yeah, but I thought we can see from the graph, it's kind of like 100 years.
100,000 years. Yeah, the longest of those is about 100,000 years.
100,000 years. I thought the Earth is spin around. Is that what it says? With the sun acts as the surface of the Earth.
I'm sorry, I can't quite hear you.
So is your question, does it correspond to a flipping of the magnetic poles?
Yeah.
No, it's not the magnetic poles. It's either the rotational axis of the Earth wobbling or wobbling of the orbital, basically precessions. There's two orbital ones. One is the precession of where is winter along the orbit with regard to the Sun. Is winter on the closest approach, which would be warmer then, or is it on a far approach, which would be colder? And then there's also a sort of oscillating squashing of the Earth's orbit, right? So it kind of goes like, if you think of it like a pancake, it sort of would go up and down like this. So it will ultimately expand and then go like that. So those are the three main cycles. Nothing to do with magnetic poles, though. Nothing to do with magnetic poles.
Okay, I think we should stop questions now. We have a 10-minute break. Can you please make it 9 minutes?